Recent reports confirm that CATL, the world's leading battery manufacturer, has launched a new generation of sodium-ion batteries featuring a revolutionary 1,200 kilowatt charging rate. This 12C capability was previously thought unattainable, and honestly, it signals a pivotal moment for energy storage. Unlike CATL's earlier hybrid designs, this iteration appears to be a pure sodium-ion system. The technology is now emerging as a serious threat to lithium-ion's dominance, offering not just cost advantages, but also a charging speed that could, really redefine EV convenience and finally make refueling an electric car as quick as filling a gas tank. CATL is not alone in driving this innovation. Other major players in China, such as BYD, are also advancing rapidly. This puts battery manufacturers in South Korea and the United States under increasing pressure to keep up. The pace of development in China is particularly noteworthy, as it underscores the country's dominance in the battery sector and its determination to stay ahead of global competitors. A key example of this new technology in use is Huawei's EV line. The model, produced through a joint venture between Huawei and another company, will feature CATL's sodium-containing battery pack. This joint brand, operational since 2021, combines manufacturing expertise and platform design with Huawei's software and components. Vehicles equipped with these sodium-ion batteries are expected to enter the market soon, bringing cutting-edge charging technology to consumers. The capabilities of these batteries are particularly striking. A slide from a recent presentation highlighted the 12C charging feature, meaning a battery could theoretically achieve a full charge in as little as 3 to 4 minutes. Such speeds represent a breakthrough comparable to the leap from dial-up internet to high-speed broadband, setting a new benchmark for energy storage systems. Two configurations of the vehicle are planned, one using a sodium-based battery and another fully electric model utilizing CATL's advanced battery pack. This pack, also known as the third-generation design, achieves an energy density similar to Tesla's 4680 cylindrical cells at approximately 255 watt-hours per kilogram. CATL claims it can fit more cells per unit compared to Tesla's design, potentially increasing the vehicle's overall range. Early reports suggest that vehicles equipped with this battery pack could achieve ranges of up to 1,000 kilometers on a single charge, making range anxiety virtually obsolete for most drivers. There is also mention of a condensed sodium battery featuring advanced thermal electric separation technology. This condensed battery is said to have an energy density of 450 watt-hours per kilogram, substantially higher than standard lithium-ion cells. An 80 kilowatt-hour battery of this caliber could provide over 800 kilometers, or roughly 1,300 kilometers, of driving range. While these condensed batteries are not yet widely deployed in consumer vehicles, their introduction would represent a significant shift in electric vehicle performance. Perhaps the most revolutionary aspect is the 12C charging capability. A 100 kilowatt-hour battery pack capable of handling 1.2 megawatts of power could be fully charged in under 10 minutes. This unprecedented rate of energy transfer would require significant advancements in charging infrastructure, from power grid enhancements to new cooling and cable technologies. CATL's latest innovation is a testament to the company's relentless pursuit of progress. The first generation was already considered one of the most advanced lithium iron phosphate batteries in the world, but the second generation pushes beyond that reputation. With the ability to exceed 1.3 megawatts in charging speed, it challenges the capabilities of any battery currently on the market, including those from leading Western manufacturers. This rapid development raises questions about infrastructure readiness. Charging stations capable of delivering such massive power levels are not yet widespread. Most high-speed chargers today max out at 350 kilowatts, a fraction of what these new batteries can handle. The industry will need to adapt quickly to make full use of these capabilities. Innovations in grid technology, energy storage, and thermal management will all be necessary to support the shift to ultra-fast charging. The implications really do extend beyond just passenger vehicles. Batteries with these kinds of characteristics could honestly revolutionize freight and logistics. Think electric trucks, buses, and even heavy machinery. Sectors where charging time and energy density are absolutely critical stand to benefit immensely from sodium-ion technology. The ability to recharge large battery packs in just minutes, rather than hours, could make electric freight vehicles as efficient as their diesel counterparts, all while reducing operating costs. Additionally, the advantages of sodium-ion batteries definitely extend to grid storage solutions. Their fast charge-discharge cycles, low cost, and tolerance for temperature extremes make them ideal for stabilizing renewable energy sources like wind and solar. As the world transitions toward a low-carbon future, affordable large-scale energy storage will be critical, and sodium batteries are really well positioned to fill that role. The next few years will determine just how quickly sodium-ion technology can be scaled for mass adoption. CATL has signaled that these advanced batteries will begin appearing in electric vehicles within the next 6 months. If this timeline holds, it will be one of the fastest commercial rollouts of a new battery technology in history. The combination of rapid charging, high range, and lower cost will make these vehicles highly competitive and, honestly, could reshape consumer expectations worldwide. International competition is certain to intensify. Companies in South Korea, Japan, Europe, and the United States will need to accelerate their research and development efforts to keep pace with China. The unveiling of CATL's next-generation sodium-ion battery technology represents far more than an incremental advancement. It heralds a fundamental paradigm shift that could reshape the global clean energy landscape. As competing manufacturers respond to this technological leap, we will likely witness strategic alliances, licensing agreements, and revolutionary manufacturing processes emerging across the industry. Established battery giants and startups alike will be forced to rethink their research and development roadmaps and production strategies as they attempt to bridge the growing technological gap. This innovation challenges the foundations of current energy storage paradigms by delivering ultra-fast charging capabilities and energy densities that rival premium lithium cells at potentially lower costs. The implications extend beyond faster charging electric vehicles to the democratization of clean transportation through reduced battery costs and the elimination of range anxiety. It also opens new applications for electric propulsion in sectors like heavy freight, aviation, and marine transport, previously considered impractical due to energy storage limitations. The inherent advantages of sodium-ion chemistry, like superior performance in extreme temperatures, enhanced safety, and the abundance of raw materials, really position this technology as a cornerstone for the renewable energy revolution. CATL's breakthrough arrives just as global markets are hitting inflection points in electric vehicle adoption and renewable energy deployment, which means this technology could, rapidly become the new standard. The convergence of these technical capabilities with growing environmental imperatives and shifting consumer expectations, it creates perfect conditions for mass adoption and could potentially accelerate the global transition away from fossil fuels. This is not simply about better batteries. It's about enabling a whole new energy ecosystem where clean, affordable, and convenient power becomes universally accessible, fundamentally changing how we think about transportation and energy storage. The true significance of this breakthrough, honestly, extends beyond just technical specifications. It really represents a fundamental reimagining of what's possible in our global energy future. I think future historians may even identify this as the turning point that accelerated the clean energy transition from theoretical possibility to practical inevitability. This innovation challenges long-held assumptions about the limitations of battery technology and, it rewrites the rulebook for energy storage solutions. So, it redefines consumer expectations about electric vehicle convenience, transforms the economic calculus of renewable energy integration, and honestly, opens new frontiers in sectors that were previously constrained by energy storage limitations. This breakthrough really demonstrates how technological leaps can reshape entire industries, forcing competitors to innovate rapidly or, risk obsolescence. The benchmark set today will likely catalyze new waves of research and development across material science and energy system design, potentially yielding unexpected breakthroughs in adjacent fields. As this technology matures and scales, it may become the foundation for energy solutions we have not yet imagined, from fully electrified transportation networks to decentralized microgrids in developing regions. The true legacy of this advancement may be measured not just in its direct applications, but in how it expands humanity's collective imagination about what is achievable in the clean energy transition, inspiring a new generation of innovators to pursue solutions to currently insurmountable challenges. While the immediate output of this breakthrough, a battery capable of unprecedented charging speeds, is itself revolutionary, Its most profound and enduring value may lie in the paradigm shift it represents. This achievement serves as a powerful testament to human ingenuity, demonstrating that with focused determination and scientific courage, even the most deeply entrenched technological and economic barriers are not insurmountable. For decades, the architecture of our energy future, particularly in transportation, has been constrained by the perceived limitations of lithium-ion chemistry. We have operated within a framework defined by trade-offs between cost and performance, between energy density and charging time, between scalability and resource scarcity. CATL's sodium-ion battery shatters this constrained narrative. It proves that the path to progress is not merely one of incremental refinement, but of fundamental reimagination. By turning to abundant, inexpensive materials and re-engineering them for elite performance, we are witnessing a move away from a paradigm of scarcity to one of potential abundance. This breakthrough, therefore, is more than just a new product. It is a beacon of possibility. It validates the pursuit of alternative pathways and challenges the entire industry to look beyond the established playbook. It suggests that the goal of a truly sustainable, efficient, and accessible energy future is not a distant utopia, but a tangible reality being built in laboratories and factories today. The true legacy of this innovation will be measured not only in the miles driven or the minutes saved at charging stations, but in the countless future technologies it will inspire, as it boldly declares that the boundaries of what is possible